Yeah.
Hello everyone and welcome to our final project presentation. We will start with the ErinsBrook geology and mining selection. Switch. Okay, ErinsBrook is a large tabular breccia volcanic, which the geologists call EOCG. So it's copper and gold and silver commodity. It is a large volume and low grade deposit type. And because of that, we first think it is an advantageous choice to choose a bulk method because there is no need to be selective, and we have a fairly consistent thickness and grade, um, and which is appropriate for a bulk method. Also, we finally choose a sub-panel caving method because we believe it is achievable according to the geomechanic characteristic, and it is also a low cost and high productivity method. Switch.
Okay. In analyzing an ore body, we have to consider what metal prices or what prices we're going to set our metals at. So we had a consensus between or a combination of long-term historical averages and consensus prices. So what that means is we looked at historical prices of all the metals involved, so copper, gold, and silver. And then we also looked at other technical reports to find out what prices were used in those technical reports for the same metals. So combining those two approaches, we derived or we came to the conclusion that we will set our copper price at $2, 2.8 US dollars per pound for copper, and then for gold will be 1,400 US dollars per ounce, and for silver will be 18.5 US dollars per ounce.
Okay, for the cutoff, uh, we start as a first approach with the Taylor 9072, which is little dated. We calculate the break-even cutoff, uh, which it is $42 tons. So this cutoff mean if we have a block of ore up to $42 NSR, it will cover the cost of the mining and the processing and the overhead costs and the transportation in this case because it wasn't included in the NSR. We also have an internal cutoff, which is pretty much the same but without the mining costs. That's mean if we are developing and we are mining in a way this drift, we can have the flexibility to keep the ore at a lower cutoff. We also study other methodology as optimal cutoff NSR, which is a more evaluate, more developed cutoff methodology, which take into account the market and the mining limit. It's also good to know there's also NPV analysis, which take into account the factor time. Um, and in a sub-level panel caving method, cutoff is also a measure of the acceptable dilution in order to stop the stope. So that means it needs some flexibility and adapted grade control process as sampling procedure and monitoring. Switch. For the production rate, we also use the Taylor method to approximate a mining life of 17 years and a production rate of 7,300 tons per day. Switch.
So for switching gears to mining infrastructure, so we for our infrastructure in developing our mine, we have decided that we are going to establish a ramp just because of the way the geological geomechanics and the way our ore bodies are. So, um, and the kind of mining method that we have decided to use. So a ramp is definitely important, and it will be used to transport ore waste when we are developing the initial ramp access out of the mine. And also we have decided to use a shaft transport system as well when we go into the full production phase because of the steeply deepening of our ore bodies and the large vertical extent of our ore bodies. And also we predict a very high production rate for our mine. To complement the shaft, we would install or establish a conveyor belt system. Again, this is required so that we can maintain our high production rate of 7,000 tons per day. The conveyors are an excellent means of transportation, which helps promote and maintain our high production rate.
Okay, so on this section, I will explain you the configuration of our installation and mine service and infrastructure, and also will describe one great optimization that we are proposing, the ventilation on demand. So basically, the mine will have the decline and all the level on the footwall, and all the other installation also would be placed in the footwall. We also have an ore pass, multiple ore pass, to join the crusher and the conveyor to the shaft. We also have a workshop and sump. The ventilation of the man, it's a great optimization that we are proposing, and it will be part of a short-term planning process, which will track machinery and staff tracking in order to optimize stope and production safety. In the panel caving, the active production should be localized in 3 or 4 levels at a time. So depending of the caving progression, so the ventilation on demand can be useful because instead of manually opening the ventilation where you are working, it will open by itself. So if we have other activity far from those main active place, the ventilation will open automatically, which is super safe. And the big size of the infrastructure justifies this optimization switch.
So as Maggie mentioned earlier, she talked about ventilation. So ventilation systems is definitely required for all the workers working in underground mines so that they can be provided safe and clean air. Also, we will require an electrical system. Now, this is a system that would help power up the mine, so provide electricity to all of the mine offices, the operations, lunchroom, washrooms, and other office facilities. Will also require compressed air. Would also require a watering and dewatering system. Now, there are many sources of water inflows and also and probably outflows in the mine, so which could include drilling, groundwater, ventilation, and sumps. We also require a maintenance and equipment workshop. Now, the mine most likely would have a maintenance equipment workshop where miners or certain types of quick maintenance activities can be done. And last but not least, we will require to have a refuge tank. Also, by law, this is mandatory. Refuge stations will be used for in cases of an emergency, such that workers can seek refuge and be safe in these areas while an emergency is going on.
Okay, in this project, we also did one dimensioning for the crusher chamber using the art of rule of the stability graph method using the Q system. So we obtain a crusher chamber of 20-meter lateral span and 20-meter height with the support category who is falling into the support category 3 with systematic bolting with an average spacing of 2.7 and 5-meter length, with fiber reinforcement sprayed concrete of 5 and 6 centimeter. That might seem like a lot, but because it is a permanent infrastructure, the crusher chamber meant to stay a long time, and we have RSR low, and even if the rock mass quality is usually quite good in the deposit, we still have all of this ground control. And it's all important to notice also, it's important to analyze the following stress condition and to monitor it, because stress are likely to increase to the undercutting and the cave growth. Switch.
Okay, now moving to some design work here, stoping details. We have decided to go with a transverse layout. This is because it provides better stability in the long term. It ensures that all of the ore is recovered. Now I also chose a ring design, which is a 10-hole ring pattern, and then the hole diameter would be 102 millimeters. Now here is just a quick diagram of what the transverse layout looks like. We have a slot drift. We have where our ore body it's gonna reside, and we have some drifts, and the production drift and the perimeter drift and the level axis. And now for mining sequence, the mining method that we chose is a sub-level caving mining method, which is a top-down mining method. So our direction will be from top to down. And for our arrangement, we have decided to go with the lead lag mining arrangement, such that we are able to operate this mine most effectively and reduce any structural instabilities in the mine. This lead lag arrangement would be conducted at a face angle of 45 degrees to optimize production. Next.
Okay, for the equipment, equipment selection, first for the first phase of the mine development, ramp access and sublevel, we will use a jumbo, a scoop, and the McLean, info charger, and hauling truck. Switch. For the shaft development. Okay, no, for the bolter, we're also gonna use a bolter for the ground support for the development. And on the picture, you see the loop truck. You're never gonna see a loop truck as clean as it is in the picture. Switch. All right. Okay, the shaft development, we choose to use a vertical shaft sinker. Switch. For the production, we're still gonna use the jumbo and the scoop and the bolter and all of the stuff from the development, except we're gonna also add the long hole drill, sandbag, and also a conveyor to reach our production rate. Switch.
So Maggie just spoke about the different equipment that we have selected for our mine, and here we just do a quick analysis or an estimate of what we expect our cycle time should be for our LHD, our scoopers, and also the haul trucks. So in our analysis, we considered different phases and different times in different phases, considering different operational criteria. So, for example, we considered a phase of loading time for LHDs as well as the haul trucks. Then we also considered tramming to the truck, dumping to the truck, tramming to draw point, and the efficiency factor. We considered these phases and took the times for each phases, considering all of the different operational criteria or parameters that we face in these phases. And that's why we came up to a cycle time for an LHD to be approximately 6 minutes. And then for our haul truck, from bottom to the surface, we came up with a cycle time of 63 minutes. And now we're moving on to our mine scheduling. Now our mine will be scheduled based on two phases, the pre-production and the production phases. In the pre-production phase, this is when the ramp access, conveyor system, sublevels, shafts, and other infrastructure such as ventilation, refuge stations, and dewatering systems are all established. Now, though the pre-production scheduling might be simple or maybe may depend on the number of phases, there are always several constraints that we need to consider when we design our mine schedule for our pre-production plan. The first one is the logistical constraints. Now, like I mentioned earlier, our mining method is the sub-level caving mining method, which is a top-down mining method. We are constrained by this arrangement. We can go the other way around. We also have geotechnical constraints. This could be as a result of the type of material that we are working in, if it's competent or not. Also, we have infrastructure constraints, which could be due to ventilation or dewatering stations or sumps or refuge stations or egresses. Now, we have just showed here our sample pre-production schedule plan. It basically lists everything based on the order of their priorities and the type of waste, type of material that is being developed, and the schedule of the scheduled dig depth of how much we're supposed to go. And now for our production schedule, this phase would occur after all of the pre-production or most of the pre-production phase has been completed. When creating a production schedule, it is very important to make sure that the number of available phases is far greater than the number of active phases in order to avoid operational delays. Now, similar to pre-production phase, we do have several constraints as well, such as the logistical constraints, as mentioned earlier. Sub-level caving mining method is a top-down mining method. We can't go around that. We also have geotechnical constraints, which could be hazardous to the miners or equipment. We also have infrastructure constraints, such as ventilation as well, other kind of services, egresses, and safety bays. Here we have also showed how we design our production schedule. Again, just like the pre-production is based on the priorities that we've set for each level, the grade, and also the effective tons that we expect from each level. So based on all of this, we can create an optimized plan such that we can optimize our NBP in the long run. Thank you for listening to our presentation. And if you have any questions, post in the discussion forum. Thank you.
Thank you.